just go ahead and basically just going through two of the most iconic like separation algorithm. One is the one that's being implemented in Liberosa, and the other one will be a state-of-the-art one that sounds much better. But it's also very easy to install. Just install it through pip install, and you can pretty much get it. You can use it in command line, you can use it in Python, and it offers really good quality. Even though the separation stem is just it's always the four. So what's the four? Vocal, drums, bass, and everything else. So it's sort of like the default way people do stuff. Cool. Where did we stop? So basically last week we would go over some of the reason why we're doing source separation and sort of give it a high level idea of what source separation is doing. So, just to recap, that source separation does not remove effects. So usually, typically, you will have something that's, dry signals coming in. So basically, sounds that's just recorded directly, but without any effects, and then you will apply some effects. This include reverb, compression, or whatever, even guitar effects. So a bunch of different stuff that's going on. And then once you have them, and the last step, usually we will consider as just summing up all these signals. So the input will be dry signal and the output will be wet signals here. But once again, that source separation does not go all the way back to the dry signals. So source separation only just output wet signals. So you will hear reverb, you will hear all the effects. So that's how we formulate it. It just decompose that addition or the summation part. And effect removal is another different task, which is quite challenging because you have to define what's clean. And sometimes some of the instrument is never possible to record a clean sound. Talk about applications. And I think we stopped somewhere here that we were talking about Moises. So free Moises Pro license until summer 2025 for emails. So be sure to sign up. And you can use it for your project or whatever things you like. Doesn't need to constrain it in this class. You can use it whatever way you like. Cool. I kind of forgot where we stopped at, but did we talk about these? Nope. Oh, yeah. Okay, cool. Then I guess we could just look into it. So today we will talk about how, source separation work in some sense. But we won't sort of like dig into all the details about what's the best model to do it, but sort of give you an idea how it works in a more high level understanding. So basically, the mathematical formulation is just simple, but also confusing in some sense, where you just have like a mixture, which we define as X, and then you have a bunch of sources that's, S1 to S5. And somehow this is the only thing you get, X equal S1 to S5, the summation. And, so your goal is to solve this, equation that, and you can immediately realize that there are infinite combination of how these S1 to S5 can compose into X. So, mathematically, it's a very ill-posed problem that we call. You can also put it into this form that just a summation. Sometimes you see this, but, it's basically just a different way to say the same thing, but it looks fancier. So source separation is an ill-posed problem. So there are always, more than one solution to this equation. So basically, there are like infinite possibility of these equations. So the key of source separation is not in how you sort of like approach it mathematically, but rather is like, what's more likely than others for these S1 to SN based on your prior knowledge. So if you know guitar, you sort of like, you know guitar sounds and you know what drum sounds like, and you will now see the challenge of like if there's a totally new instrument that you don't know what it sounds like, then source separation could be the very challenging problem in that case. So, source separation is always talking about, the bias, how we know these different instruments sound like. That's the key why source separation can be done. So, this is homework 2, I guess. So, we look at these, spectrograms. So somehow from the spectrogram, you should be able to sort of like guess what these sounds would be like. So, trumpet will always have this harmonic structure that, because this is, when your y-axis is linear, then you get this harmonic structure that's, the partials and or the harmonics. So this would be the basic frequency 2 times, 3 times, 4 times. That's how you have that harmonic sounds. So it sounds like, well, that's what we have. And the vacuum cleaner, it's just a bunch of noise because it doesn't have any pitch. Kind of there's some pitch here, but it generally doesn't have a general ideal pitch, and there's no vertical lines, there's no percussive, vacuum cleaner is another percussion. Whoops. Stability, flat, smooth, and noise. And for drums, you will see some of the vertical patterns because that's the percussive sounds. So whenever you hit a hi-hat or a cymbal, that just generate that sort of like very short noise in some sense. So if you look at the noise, and if you look into some of the drum machine, sometimes those, hi-hat and cymbal, you can actually just use a very short noise, filter noise to get that sound. So drum has that vertical pattern that sounds like, explosive, percussive, transient sound. So you see that those vertical pattern, but you also see some because the drum, if you play the drum like the kick or the snare, you do have some pitch, you can tune it. So at the lower frequency part, you still get some harmonic like structure, but in general it's much lower frequency, but the key would be vertical patterns. Did you get it right in homework 2? Cool. Cool. So, if you look for, as many spectrogram as you can, then you will sort of get a sense that, somehow human has the ability to sort of like, well, how does this generally sounds like? It's very hard, it's possible, but it's sort of like never possible to actually know what the note is. But you can sort of get a sense that, well, this will be more, harmonic like, and there will be some pitch, this will be noise, this will be more percussive. So that's the key of source separation. So now you see that why some of the models do really well on drums, because drums would be much easier in this case because drum has its own pattern, and all the harmonic instruments has its own way of doing it. So this brings us to one of the most iconic way of doing source separation, which is time frequency masking. So imagine we have this sound. Can Zoom folks tell me whether you can hear this sound through my laptop? You did? Okay, cool. So it's us suffering somehow. um, Cool. So this is time frequency masking. So what we want to do here is that just stare at this spectrogram, and what we want to do is, source separation. What we want to do is to, well, it's not working. To come up with, decompose it into 2 different channel. So imagine in this case, it's just sound. So I believe this is not the ground truth. This is one of the algorithms outputs. So Not perfect. And this. So what we want is, just two different track. Um, but I can actually hold this up. Anyway, this way. So you can look at that, something that you want here wants to go to this channel. That's the more percussive one. And these harmonic one should go to this. So if that's our goal, you want to separate it into two channels, which one is more harmonic, one is more percussive in this case. So if you look at how we do it, one of the most iconic way is through time frequency masking. So basically what we want to do is to do, sort of like binary classification. Look at each, time frequency pixels, say this blue one, we just decide which track it should go to. So this case, it should go to the percussive track. And, if you look at this green one, it should go to the harmonic track. So this will be 1, this will be 0, and in the green one, this will be 1, and the bottom one will be 0. So that's the way, the simplest way how we do time frequency masking. And so you can think about it as, just a classification on each time frequency being. And we do it through the whole time, the whole spectrogram. So that's sort of give you the sense how source separation can be done in the most simpler form. So if we have a spectrogram and we just do this source separation model, and it's actually not doing waveform decomposition, it's actually just predicting some mask that for each single TF bin or time frequency bin, so each little pixel in your spectrogram, you want to see which track it corresponds to. So in this case, if we're doing like two track, separation. Once you're done, you just apply this mask to your spectrogram, and this will be something you get. Does it look like something that we got? I think I put in the wrong image. It doesn't look like. This look much more like the right one. This is likely wrong. So if you look at the bottom one, it's definitely doing some filtering that, here everything is gone. Yeah, I think I'm doing the right one. So if you look at the bottom part, you see that all these, lower frequency are being put into the percussive one, and there's no vertical lines anymore. So all the vertical lines are gone. So all the vertical lines go to the percussive part. And all the horizontal harmonic one mostly kept in the harmonic one. And this is like doing spectrogram. But anyway, you can do SDFD to get the spectrogram, and in the end, you can also do ISDFD. So there's one complexity is that ISDFD need to work on spectrogram. Here we are just showing the magnitude of the SDFD output. So there's the phase. So typically in source separation, we will grab the input phase as the phase to come accompany these things. There will be some issue, but this is how we've been doing source separation for a while. That somehow work not too bad. Questions on this? Yeah.
Like the cell separation, is it good at, well, it could probably separate like synthesizers and stuff like that aren't necessarily like we have like a specific category for each one. But like, would it be able to tell that like, okay, this is a like obviously like this is a trumpet, this is a bass, this is this, that, and the third. But like, would it be able to tell that this is a synthesizer, or would that have to be grouped into another category?
Oh, you mean acoustic versus, that's always an issue there. So that's why there's that other instrument. So it depends on your data set. And it's a smooth spectrum. Somehow at some point it will become more, synthesizer like. So sometimes if you like think about, keyboard and string and like organ-ish they have a lot of overlap. So there's no way you can sort of like define how to do it. So the way to do it, well, depends mostly on your data set, and you just apply it and you just listen to it and hope and find where it is somehow. So if you don't actually need good separation on those two instruments, then they could just combine into one track. If you do want them separate, I mean, there's no way, no easy way you can tell whether a model can work on that or not. So think about one classic example is like string quartet, like violin one, violin two, first violin, second violin. How do you know, like separate them? I mean, technically, if you to it carefully, listen to the bowing, listen to the characteristic of the violin, maybe you could do something. But in general, that's, it could be how hard it could be.
Yeah.
And later, I don't think we have an example, but you can think about, other cases like SATV, like voice, they are pretty much all considered vocal. Or the drum examples, like if you train it in your typical way, those drum will be the same track. But if you train it differently, then those drum could be separate, bass drum and stuff.
Right.
So it depends a lot on how you train it, and most of the time it depends on your training data. But fundamentally, they can be very ambiguous. There's no way you can avoid that. Yeah. Cool. So I guess we will just go over one of the traditional approach that we will work on in homework 4. And this just to give you the hint why cell separation can work and what's sort of the underlying concept of cell separation. And once you enter the deep learning era, it's like everything is just black box. You're just trying to develop fancier model to do it better. But there's still some underlying concept of why cell separation can work at all. So this will be something that we will look into. So this is percussive harmonic source separation. So this is one of the very classic algorithm in source separation that want to, use heuristic to separate percussive and harmonic instruments. In some sense, you will see how it works. So by looking at these spectrogram, so hi-hat, snare, kick. So these are clean recordings, so there's not much reverb. So you can definitely see that there's a clear difference between percussion instrument and other pitched instrument or harmonic instruments. So you can see that percussion usually have vertical shape in a spectrogram. And on the other hand, these harmonic sounds tend to look more horizontal in a spectrogram, but it also have that, repetitive pattern. But in general, it look more horizontal in some sense. So, HPSS, which is harmonic percussion separation, basically just try to leverage this idea to do some sort of like harmonic versus percussive separation. So how it works is that we apply a medium filter over the time axis so that we can get the percussive pattern. So this will be the input, spectrogram. And now here we are applying different horizontal medium filters. So the show bar here, the blue bars are the filter that we are applying to the spectrogram. So we will just grab this and then apply it in different place. And then we will keep the middle point as the filter point. So that's why if you look at, W equals 31, here, sort of like all the vertical patterns are gone. Because if you apply, let me just write something. So how do it work? Did I have it? Oh yeah, I have it. So this is like W equal 5. So you have width of 5. That is the your filter. And then when you do the median filter, it still have some value. But once you use a larger filter like this, Then when you take the median, it will be mostly the, zero value, so that you get rid of all the vertical stuff. That's good. Cool. So, this is how we sort of like get rid of the harmonic part, the percussive part. So keep it in mind. And now we can sort of do the same thing, doing on the vertical side. So now if we apply a vertical filter to it, so this is much harder to see because there are too many, high level, higher frequency component. If you zoom in to the lower frequency part, then you can sort of like see those, harmonic patterns here. So what you would do again is that applying these vertical filter to it. So when it's W equal 5, then you sort of like still get the same shape, because when you are applying that medium filter, it doesn't have that smoothness effect. But when you apply a much larger medium filter, then you sort of like make it blurry on the vertical side. So you can think about the medium filter just a way to make it blurry, but just across the temporal axis or just across the frequency axis. So, applying the median filter over the frequency axis makes harmonic patterns less prominent. So you can sort of like smooth things out and everything just gone. It just becomes so smooth in the frequency part, just becomes something blurry. So, this is the idea behind harmonic percussive separation, but, in the end, you won't be just like turn this ISDFD on this. If you turn it back, it will sound like vacuum cleaner because it will be noise because you remove all the harmonic structure. So how harmonic percussive separation work is sort of like leveraging that idea, but make it into a mask. So, we have this horizontal medium filter. So we have some input spectrogram and we apply this horizontal medium filter. So we sort of like get rid of, the vertical lines. And then we apply the vertical medium filter. So we sort of like get rid of, the horizontal line, or, it's not get rid of those, it's like make it more blurry. And now the key is here that we're doing this comparison, that if the harmonic part is larger than the percussive part, then we get the first mask. So this mask would be a 1 if you have something in this larger than something in this. So you can see that the mask pretty much just get all the horizontal pitch. And when you do the other side, that, if the harmonic part is smaller than the percussive part, then you get the percussive mask. So if you look at the percussive mask, you see all the vertical structure. And if you look at these horizontal line, it's still there, but these horizontal line is actually the opposite. It's the places where you don't have the sound. We'll see later. But this is basically how harmonic percussive separation work. This is in 2010 and 2014. So it's quite before the deep learning era, but it somehow still have that understandable approach of doing stuff. So once you get this mask, you apply the same idea that you have your spectrogram and you just times that mask so that you get rid of the percussive part. So, look at these. We won't be doing ISTFT on this because it would just make everything blurry. But now you get the mask and then you apply it on the original spectrogram. So you keep all the details, but somehow you do separation in some sense. And the same for the bottom one. So that, you still have that, resolution on your spectrogram by applying mask. So you can definitely see somehow here that, the harmonic patterns still here, and the harmonic patterns are sort of gone in this case. And again, SDFD and ISDFD if you want to get the waveform back. Cool. Any question here? Just way of doing harmonic percussive. There's no assumption what these sounds are. Just looking at, it's vertical or it's horizontal. That's it. So if you look into these spectrogram, you will see that when you are doing, harmonic components and percussive component separation, so these are the mask. So these will be the input. So what you get is that, the percussive part would be in the percussive component. And if you look at the harmonic component, if you zoom it in into, just 0 to 2000 hertz, then you will see that for the pitch that you have, or, horizontal line, it will be in the harmonic component, but in the percussive component, it will be the opposite. So, in the mask, you see these horizontal lines is actually the opposite of what we want. So the harmonic component will keep those, horizontal components, but percussive mask will just keep those, the black, the places where there's no value. But you can also sort of look at this part where you have the harmonic component. This is the bass drum. So very low frequency, but you still see that, harmonic pattern. So you will get something in the harmonic component rather than the percussive one. So this is also the complexity of drum, kick drum. Looking at the bottom part, it sounds like bass. So, kick drum has both the, percussive component, but also, the harmonic component. So that's the complexity here. Cool. So these are the results. So we can look at this. So this will be something you will be doing in homework 4, but mostly just calling librosa.decompose.hpss, and you will get these. So this is like a example. We can listen to it. So this will be the input mixture. I think it's the same song. Nope. This would be the harmonic part. This would be the percussive part. Well, so you get a sense what it sounds like. It's just like doing some sort of like separation, but it's not so clear what we are separating because, again, there's no any assumption of what we are doing. This is just pure heuristic. Just looking at the vertical lines and horizontal line. This is the best we can do in some sense. So if you look at it, so again, these percussive sounds will mostly be preserved in the percussive part, all the vertical lines. And for the horizontal, more harmonic-like structure will be kept in harmonic component. And for, percussive part, it's mostly just these blurry things, blurry patch. So these blurry patch, you can think about it just like vacuum cleaner-ish sound. It's mostly like a very low intensity noise somehow. Cool. So this is another example. This will be the input. So just drums. So, but if you apply HPSS on that, you will see that it actually captures some of the drums, not the cymbals as harmonic component. So you can think about it, it's not perfect, but, it's sort of like through this algorithm, what's considered as pitched, and, everything else will be in the percussion. So everything vertical. So you can definitely see that there is this like horizontal line where, it's sort of like have some you know, pitch-ish like thing going on still in the drums. So this is what best we can do without any pre-assumption. So this is like harmonic percussive source separation, and you would do it in homework 4, even though should be pretty simple. Just liberosa dot decompose dot hpss. I can put it up actually real quick. So for homework 4, it's just, two part of it. So the first part would be just doing harmonic HPSS using Librosa. So you load the some sound, you do STFD, and this is the key. That's pretty much just it. H P would be the HPSS output. So librosa.decompose.hpss. So this is pretty much what you need to get HPSS Browning in Librosa. And once you've done it, you first convert it into, dB decibel so that you can plot it. But if you want to get it back, you can also use ISDFD to turn these spectrogram back to the original sound. So, this is nice. Basically just the samples that I show. So that's pretty much the first part. What you would do to be quite easy, just run it on another example and plot the spectrograms. And the other one will be, get the waveform back and then try to remix it, that the harmonic component will be reduced to 10% of it. So, less percussion, basically, less drums. So you can sort of get a sense how these could be used if you want to sort of like remix stuff. Cool. Any question on this? Nope. Then let's move on. So nowadays things are mostly deep learning. So the Moises Pro, the stuff that you see, why it works so well is that they are using deep learning in some sense. So deep learning, as you can see in the samples previously, is that if we are just doing heuristic, there's no way the model can sort of like understand, well, bass drum is part of drums, even though it does have that pitch component inside it. So deep learning is the way to go, because you can give it a lot of like example audio so that the model knows that, well, bass drum, if it sounds like something that a little bit percussive, but also have that bass component in it and sort of like combined together, then it will be a bass, it will be in the drum track rather than in the bass track. So it depends on how you tune those stuff, and depends a lot on the data set that you have. But in general, how you approach it in deep learning is, not so interesting because, in terms of how you train it, the key in source separation, I would say mostly in how you prepare the data set rather than, the model itself. There's a bunch of different model, but in general, model-wise, what we want to do is that, we are given some spectrogram. We want to use some neural network to separate it into different spectrogram. And in this case, these are the ground truth spectrogram of the 4 tracks. So now you can sort of like see why it could be very hard for the model to do it. Because, looking at these, it's like thinking about harmonic and, passive spectral separation. There's no way, without understanding how these instruments sounds like. If you don't understand those, there's no way you can guess what these components would be from the mixer. So again, this is a very EO post question that problem that there's no way for the model to know without some bias from your data set. So basically what you want to do is that, you predict a bunch of different sources and then you have some ground truths. In this case, I just grabbed the ground truths because I don't know how to make something that's, sort of like ground truths, but not. Maybe I just do a blurry filter on it. But anyway, you get something likely that's, pretty off at the beginning, but at the end, it will sort of look like your ground truths. But anyway, how you do it is just measure the difference. So you compute the loss function. You can imagine there's different way to do it, but the simplest way is just compute the distance between these two sort of like images. So you can just do, L2 loss, which would be, basically just S1 hat minus S1 and then square and then sum it up. That could be the easiest, loss function that you can get. And then you just train the model by optimizing the model to do it. So this will be the simplest form, but there are also other different loss function and how you set it up. So, just measuring the distance might not be optimal. Sometimes we also need to look at like signal to noise ratio so that you can directly improve the signal to noise ratio by optimizing it. But basically, this is how they work. On the other hand, this is, spectrogram, but using deep learning, you can also apply it on waveform directly. So it doesn't necessarily have to do, TF, time frequency masking anymore. If you are using deep learning, you can also do it this way, just some waveform mixture, and then you predict different sources, and then you compare them with the ground truths. But the key would be how do you measure the difference between waveform? So if you take one waveform and then you delay it by 10 milliseconds, it pretty much sounds the same. Or you just inverse it, it pretty much sounds the same. So if you just do direct comparison, it doesn't make much sense because it just become equivalent. It doesn't make much sense if the phase just off for a little bit. So if you want to measure the difference, people have come up with different way. You can even do SDFT and then compute the loss on the SDFT. And somehow, because SDFT is a continuous transform, so you can actually make SDFT differentiable. So you can actually train something based on the SFT loss function. So, there's different ways to do it, but somehow if you can figure out how to define the loss function, you can, again, train the model. Cool. So this will be the model that you will be experiencing in the homework. It's in 2019, but it's still working pretty good in their setup. I mean, if it's just vocal, drums, bass, and everything else, then it somehow do pretty well in a sense, because these are the simplest track that you can extract and less confusing. So what it does, if you stare at this model, it seems quite chaotic. But usually what you want to do whenever you see such a model, the only thing or the first thing you should do is try to figure out where is the input and the output. Because, again, all the deep learning models are just some functions. So it's a mapping from your input to output. But people are so creative that, some of the models that sometimes you see the system architecture, you never get to tell where the input and outputs are. But anyway, in this case, you will realize that it's going from the bottom to the top. Sometimes it's going from the top to the bottom. Sometimes it's going from the bottom to the top. But anyway, you should figure it out by looking at the arrows. So, in this case, our input will be some mixture. This is like some waveform, and the output will be 4 different waveform that's, just different tracks. So one will be vocal, one will be bass, one will be drums, one will be every other instruments. So these are the inputs. This is the input. These are the outputs. So that's what we get. And we have this like chaotic, gigantic model in the middle. So if you zoom into it, I mean, on the paper, if you look at it, these are, the encoder. So encoder feel much more friendly in some sense, because you see some friendly stuff, convolutional 1D, ReLU, we know ReLU, and GLU might be something new, but, it's still a convolutional neural network. And if you look at the shape, it's pretty much the same shape. So you can sort of like just ignore it. So, basically it's a convolutional neural network that turn it into a smaller resolution, and there will be some other function that do the convolution again, and then do GLU is just another activation function. So we'll do a convolutional layer that doesn't change the shape of that. So, you downsample it through a convolutional layer and then you keep it. And if you look at all these encoders, there are several. So it will just shrink the size of the waveform smaller and smaller until in the bottleneck layer. And for the decoder layer, if you look at it, again, it's just convolutional layer that, it somehow would have this like convolutional 1D thing. And then you have the convolutional transposed version of it. So basically it will increase the size, the shape of your waveform. So, you can think about this as like encoder, just as encoders. So encoders will have the waveform and then sort of like compresses, reduces resolution. And in the end, during the decoder part, it will just expand it again. So upsampling again back to the original waveform size. And if you look at it, you will realize there's a bunch of these errors. So that's what we are going to talk about next. So this particular structure is called UNet. So I guess there's so many complexity. There's still this LSTM that we won't talk about it. Just assume that's something happening in the middle. And in the future, when we talk about music generation, that's where we will talk about LSTM. But for now, there's something mysterious going on in the middle. But I guess for here, what we want to know about, so think about this course as, introducing to some of the cool deep learning models by examples. And, unfortunately, some of the models, they are too complex. There are too many components. But anyway, hopefully we can get UNet, sort of give you the sense of what UNet is doing in this case. So UNet is applied everywhere, I could tell you. Nowadays, all the generated models, to think about latent diffusion model, they all have UNet inside it, even though it's called latent diffusion model because diffusion model sounds more fancier. But latent diffusion model is a combination of variational autoencoder, GN, generative adversarial networks, CNNs, transformers, plus UNet and residual net. So it got everything, but somehow the name just latent diffusion model because it sounds fancier. But anyway, UNet is one of the important architecture that we should know about. So the UNet, look at this figure. This is the original figure, and look at what it is being applied. It's biomedical image segmentation. So what UNet wants to do is, this is the downsample part, and then these are the upsampling part. And, the UNet, the name UNet comes from this U shape. And there's a bunch of links in the middle. This is the original figure, and these are skip connections. And so that's why it's called UNet. But this is very hard to see what is going on. So we have a toy example of UNet. So again, this is the one that we look into in the convolutional neural network. So if you have some 16 by 16 images or image or spectrogram, but anyway, something that look like a square. And you can apply, convolutional 2D 143. So basically input channel. So you have one channel input, you have 4 output channels, and your, sliding window for your convolution no layer, the filter size is 3 by 3, and then padding equal 3, so that you will get something, 16 by 16, and then you apply maxport 2D to downsample it into 8 by 8. So anyway, once you do this pair, you will get something like this that, shrink it into, lower resolution, but increase the channel. But you can apply again, downsample the size, but increase the channel. And now, UNet, the key of UNet is that we just don't go downsample all the way down to, like a flattened vector so that you can do classification. But rather in UNet, we do the opposite. We want to scale it back. So UNet, think about it like a codec-ish thing. So you do encoding so that it make it more compressed, and then you decode it back into the original format. So now we do something, convolutional 2D. It's pretty much the same. So convolutional 2D A43, it doesn't change anything. So, convolutional 2D, as we talked about previously, that it will still be the same size. Will be 4 channels, and each of them will be 4 4. And then now you do the upsampling. You just you can do different upsampling way. You can just use nearest neighbor. You can also use bicubic interpolation. But anyway, you just upsample it into a larger shape. And then finally, you make it back to original one. Usually there will be additional convolutional layer after the final upsampling because you want to fix all the details. But anyway, that's sort of the idea. You have a bunch of convolutional layer and max pool so that you downsample it or reduce the resolution, and then you have convolutional layer plus upsample layer so that you turn it back to the original resolution. So the key of UNet is to have these skip connections. So these skip connections look like this, that you will just grab something here, because if you look at the shape, that you will notice that it will be perfect symmetry in UNet, where you have this 8x8 and 4 channels here, 8x8, 4 channels. I mean, the number of channels doesn't matter, but they have the same shape of 8x8. So in principle, you can actually move these or copy them as something here, so that when you are doing the final convolutional layer, you are instead using the whole these features, but also features coming from the previous downsampling part as the input. Questions? Cool. So anyway, that's UNet. So UNet, even though looking at this figure, it's kind of confusing, but basically what UNet is doing is to sort of like combine the low-level features and high-level features. So, well, I sort of hinted. So the orange one would be the low-level features because it's coming at the higher level. So when you have an image, the first, the filter, you will always get those, just like edge detection. And now once you go down deeper into the model, you will get some more high-level features. And even when you decode it back, it will still get more high-level features. So you are combining these high-level features that detect different structures, but also you have low-level feature just looking at the boundaries, and you want to combine them to get your best prediction. So this is important. At the beginning. So one more tips is that UNets are useful where the inputs and outputs have the same shape. So that's pretty much where you should use UNet. So if you look at this figure, that it's always doing this trick that you combine, low-level features and high-level features, and again, higher level features, low-level features, again and again. So these skip connection is actually bringing, in this case, it's the very first layer. That's just all the boundaries. So very low level features, but you combine it with, higher level features coming deeper in the model. So these application of UNet, so all these models are sort of based on UNet-ish. I don't think this is based on UNet, but just sort of give you the sense, depth estimation could also based on UNet. So this is the original, not the original, but like UNet is proposed for image segmentation. So sort of something like this, can you detect like humor detection? So in this case, your input and output is exactly the same shape. So what you want to do in, why do we want those skip connection is that, in the last layer, you want to get the perfect, boundaries of these. And these boundaries is not possible without all the detailed, very low level understanding. But at the same time, you want it to be, you also want some high level features because you want to group these things so that you know which part of which is the same group. So, looking at image segmentation, that, these are considered all as the jacket. So, you do need some high level understanding how these different pixels connect. But at the same time, if you want to get the boundary correct, then you have to have very low level features. So that's why in UNet, we have low level features to help you get the perfect, boundaries or all the details. But at the same time, you need high level, features so that that, well, this is a jacket. And, they are grouped together as one single larger object rather than pixel wise prediction. Cool. So these are some of the application of UNet. You can also use depth estimation where, this case, it doesn't has to be UNet, but you can think about it. It could also be UNet so that it can help on, connecting different structure. You can also just do, pixel wise, regression as we talked about previously. But if you have a UNet structure, it can sort of like understand that, well, these are all sofa pixels so that they should be in the same color kind of thing. So there's a bunch more application of UNets. So these are likely something you might be interested in. So like style transfer, but you will also see in spectrogram, in waveform, in music and audio, in different format. But these are places where UNet is being used. Style transfer. So your input and output pretty much the same shape. So when you apply UNet, there will be very local, like the shape, like whatever lines, boundaries, even the, I don't know, everything, every detail, cloud borders, I don't know. And we will be keeping this the output, but still you will have high level thing. And colorization, semantic synthesis, this is like latent diffusion model nowadays. And also this is like sim to real. This is helpful for autonomous driving. So, this is like GTA and they just turn it into a real image so that you can train your autonomous driving, autonomous car in this scenario. And it's very helpful because there's no way, you can just have some autonomous car or, self-driving car on the street and then hit someone and then we got the training data. That's not how it works. So, sim to real is a way, we have like very good, GTA, gaming engine. You can imagine a lot of way you can hit different person or imagine different cases that it might fail. But it doesn't look real. So you can apply these model and it's actually being applied a lot in industry that, you can turn these, gaming-ish screenshot into more realistic way so that you can train your self-driving car in this, virtual environment, but later you deploy it on the street. Question on this? Question on autonomous driving? I have no idea how they work anyway. Cool. So let's get back to Demox. So Demox is pretty much just a big UNet. So this is again, it's not UNet-like, but this is UNet somehow. Just pretend it's a U. So this is the U part, and these will be the skip connection. But anyway, it's just that there are some skip connection going from the symmetry part that the output shape will be symmetry, and then you can do skip connection to connect those. And so these are UNets. And that's the Demox, the first version of Demox. So in homework, you will just try it. But actually, in the homework, when you install Demox, the pip install, it's actually using this more fancier version of Demox, which is the second version, which is hybrid. So in this case, it's just waveform. But waveform is something very inefficient to work on because waveform is just huge amount of information. So in Demox hybrid, they are actually doing something, like a hybrid module where you have the frequency domain module and the time domain module. So the input again is still pretty much like this. You have the waveform, but now you added this new route. So where you have, you first do SDFD, you get some waveform, you get some spectrogram, and then you apply the same UNet, a different UNet, I mean, because different shape. And once you have all these UNet, and at the end you get the ISTFT back to the waveform, and then somehow you apply one more filter on that. So these are, sort of like decompose your model into, well, if this is something that's easier to be done in time domain, then do it in time domain. If this is something easier to be done in frequency domain, do it in frequency domain. But anyway, the output will be add back in the waveform domain, because that's what we care about. Cool. So that's pretty much demuxes. So in homework 4, you would just use it. But using it is very straightforward. You just install it by, where it is, pip install demux, and wait for the bit. But once you are done with that, there's like 2 ways to use demux. Where is my, yeah, there's are 2 ways to run demux. One way is just through command line, so you don't necessarily need to use Python. So once you pip install demux, you can just do demux some file, pretty much like YouTube DL that you can download something hacky. But anyway, demux, you will be available once you install it. Or in Python, you can also import a demux and use demux.separate.man. But this basically, these two are equivalent. So when you code this, it's just calling this. So, pretty much the same thing. And there are some common options that you will use. MP3 will be smaller file, especially useful to keep your Jupyter notebook smaller, because it will embed it in the Jupyter notebook. But if you want, the base quality, you should do waveform. But, just in case you won't be uploading something like 200 megabyte to Grayscope, it doesn't make much sense. So we will use MP3 most of the time. And source separation output is not perfect. So, you won't hear much difference in this case. But if you want to hear what the original waveform is like, just remove MP3. 2-stem modes, we will look at this, but basically it's like just one and other. And you can also force it to run on CPU only. So demux by default, if there's a GPU, it will use GPU and it's much faster. In this case, it's just 4 seconds to do a 30-second song. If you don't do it that way, you will be very slow, and that will be one of the question it's asking. But anyway, how you do it is just demux, separate, man, and you pass different arguments. So this is basically like how you do it in command line. So you would do demux dash dash mp3 dash dash 2 stems drums, and then your file name. So this is basically how you do it. And once you are done, you will find it in the output directory. So it will always create this separated ht demux hybrid demux, I guess, and this song name, and you will get everything else. So this will be what it sounds like. So if we are doing just drum versus not drum separation, this will be the drum track. So much better, and everything else. So, it's much better than the case we listen to. And this is another example where you have more stuff. I think I have it on, oops, I have it on slides. Anyway, we can listen to these. Screen sharing has stopped because the external display is disconnected. Sorry for the trouble. Cool. So, this is another example.
Hey, my baby, it's a beautiful day. Let's call into work and we'll go out and play.
Cool. So this will be the drum track. We have drums. There's the kick. Okay. Later you will hear other drums, but you also have bass track. And I guess vocal will be most obvious to hear. I think at 7-second-ish. Nope. 10-second-ish.
Hey, my baby, it's a beautiful day. Let's call into work and we'll go out and play, sweet darling.
Yep. And everything. So you go, if you think about the harmonic, percussive separation, then in this case, guitar sound would be a little bit percussive in some sense. So you can plot it and you will see this is the one that I show on slides, but and for your homework, you just do it on another Liberosa sample, and you will remix it. And something fun is that you can actually figure it out. I mean, you will anyway in the end figure out how to do it. So turn that other track goes from 0% to 100% in 20 seconds. So what you would do is just to manipulate the amplitude. So initially it should time to 0, and at the end it will be the original amplitude. So this can be done by using mp.lean space that will just give you something from 0, 0.1, 0.2, all the way to 1. But in a longer span, that it will just match the size of your input. So, pretty much you can just time this to your other track and try to remix it so that you will have that instrument coming up. So you can think about that sort of like, remixing or ways to do it. And the final question would be just testing on CPU versus GPU. It should be the huge difference, I can tell you. So on CPU is usually, somewhere around real time, but faster than real time. So 20 seconds, you should take 10-second-ish, but on GPU is much faster. So the 30-second sample, we only need 4 seconds to run it. And you can just use -d CPU to do it. And then you will use this function to sort of like measure how long it takes, time the function. Cool. So that's what we would do in homework 4. Questions on that? Should be pretty simple compared to homework 3. So no training. You should be more familiar with either Colab and Gray Lakes. So pretty much these things should be configured that you don't actually need to do anything. So what you need to do is just do the same thing, but apply it on another track and try to do some remixing and, test how long it takes on CPU versus GPU and try, deep mux versus, HPSS. That's pretty much it for the homework. There are a few slides left. We will go over that. So there are a bunch of data sets, but most of the time, if you're not, I don't know, joining in Moises, you won't be doing these. But to give you some sense, some of the data set, even if you want to use it in the future, these are some of the data set that give you all the stems and the mixture. So, if you're even doing auto mixing, doing different thing, these could also be helpful, not just for source separation. Or, if you want a data set with a bunch of vocal, then iColor is one of the way that you get clean vocal sounds rather than all the other instruments. So sometimes these source separation models are very useful because they give you stems rather than the full mixture. So these are some of the iconic one. 1K, just 1000 medley dB, 200-ish, 100-ish, and Moises DB is Moises model. They can their data set that can be open source, and you can download it on Zenodo, I believe. But there are different data sets, pretty small in the beginning, but nowadays getting larger and larger. There are also synthetic data sets. So Slack is just a bunch of MIDI file, and you just use synthesizer to synthesize it. And there's also SOD is a symphony sound. So this will be pop music. This will be symphonic sound, but MIDI file, and they just synthesize it to get a bunch of data. But you know, it's different from the real life mixture and sounds pretty different. Anyway, these are a comparison. There are some interesting system that I want to talk about in the end. So, you know, we talk about the way how people tend to think about source separation, but source separation is much more than that. We have like audio-visual source separation that you can click on video to get the sound out, but there are also different source separation things. So one thing I want to talk about is choral music separation. So, you know, choral is much harder in the case, you know, versus, you know, drums versus bass. This case, they are all vocals. So this is one of the like system that could do choral music separation. This will be the mixture.
Oh, my heart this night rejoices as I hear.
It's such a pity that we don't have speaker today.
Oh, my heart this night rejoices as I hear.
You can definitely hear there's some alto sound in the back, and this is alto.
Oh, my heart this night rejoices as I hear.
The ghost of soprano sound.
Oh, my heart this night rejoices as I hear.
In case you hear some bass and also soprano at the same time. I mean, choral separation is much, much harder than the example that we heard. This.
Oh, my heart this night rejoices
Cool.
as I.
So how they do it, how we do it, or so you know, this is through data augmentation. So the tricky part of choral music separation is that you do have some data set, but they are always not big enough. So the way how we did it is, you know, through data augmentation. So we actually figured out a way to sort of like find a way to synthesize some data set that sounds very good. So this is like the one that you get if you play it on MuseScore or whatever MIDI found. It's nothing like vocal, but if you use a much expensive, well, that's something else. If you use something more expensive, you know, a much better, you know, vocal choral VST, just a vowel. So you can synthesize much better sounds, and you know, it's if you have the lyrics, and even better. This is sort of how we did it. You can get a bunch more data. So, you know, the idea is sort of like semi-supervised learning, or, you know, transfer learning in some sense, where, well, you have like, say, 100 hours of choral data that doesn't naturally give you the best results, but somehow you can use these model, use these synthesizers to give you, you know, thousands or, you know, even more hours of audio that you can train your model. But in the end, you just fine tune it on your real data set so that you get better performance. So that's one way we can do it through data augmentation. This is not based on source separation, but I think this is pretty cool. So if you have time, definitely try it. It's very fun. It's an ML-based music harmonization model, so nothing to do with source separation, but I would do it anyway. This will be the last thing about this class. So you know, this will be the bass. And then you have tenor. Mezzo soprano. With a soprano. So, you know, the harmonization, the one you click, is you control it. Everything else is machine learning. Well, so definitely worth trying. But again, it's not source separation. It's actually a music harmonization model, but it's pretty cool and sort of relevant. But anyways, cool. Did I miss anything? I optimize the schedule a little bit. So we will be doing project pitch on March 19th. Hopefully that works. If it doesn't work, send me the message. We could move it back to March 17th. But if not, then let's keep it on March 19th. So, over the spring break, next week we don't have class. You can start thinking about, some project idea. We will have more stuff coming up before the project pitch, but think about who you might want to work with as a group and some of the interesting stuff. And we will also listen to, AI song context through the spring break. So that could give you some ideas what you could work on. Cool. See you Monday. On Wednesday.